Hey, hello everyone. Good morning. Welcome to Top Talks. And I'm Tejasri Rema along with Surya Karla hosting this session. And today we are going to have a wonderful top speaker with us. And we are going to share many thoughts along with him. And he's Mr. Dr. Sharma V.Pisupati Garu. Sir, I'm wishing you a very warm welcome to our session, sir.
Thank you. Thank you very much. And
Sir, we'll have a one prayer song. Then we move on to the intro session. Okay, sir?
okay, good.
Yeah, Jayashri Akka, can you please sing us a song?
Yeah. Mahaganapatim manasa smarami Mahaganapatim manasa smarami Mahaganapatim Mahadevasutam Guru Guhanutam Marakoti Prakasham Shantam Mahakavya-natakadi-priyam Mushikavahana-modaka-priyam Mahaganapatim Manasa Smarami Mahaganapatim. Thank you.
Thank you. Excellent. Excellent. Very good. I really.
Thank you, Akka. That was. Sir, I'll just give a brief introduction about you and then we will move on to the talk. Okay, sir?
All right. Whatever you say.
Thank you, sir. So, Dr. Sharma V.Pisupati is a professor of energy and mineral engineering, chemical engineering, and director of online education in the John and William Leon Family Department of Energy and Mineral Engineering at Penn State. He held his PhD in chemical engineering from Osmania University, MTech degree in chemical engineering from IIT, and a PhD in fuel science from Penn State University. He has been studying and teaching uh, the issues related to the energy and environment from past 32 years. He has worked in industry for 5 years before joining the Penn State. Dr. Sharma main areas of scientific research are combustion behavior of fossil fuels in fixed, fluidized, and pulverized modes, computation fluid dynamic modeling of combustion systems, of emission reduction, advanced power generation methods, oxy-fuel combustion, slagging and fouling in gasification, coal and biomass co-gasification, energy conservation methods. He was principal investigator or co-PI on 57 external funded scientific research projects and was involved in 15 other projects with specific responsibilities. He co-authorized over 170 research publications and has 1 US patent and is currently supervising 5 doctoral and 2 MS degree theses. Dr. Sharma is Dr. Sharma is very actively involved in professional societies. His service to professional societies includes co-organizer and or co-chair or moderator of 27 specific scientific and teaching related symphonia for the American Society, ASMV International Fluidized Bed Combustion Conferences, Annual International Pittsburgh Coal Conferences, and American Society of Engineering Education. Associate Editor of the Journal of Engineering Research and Technology. Editorial Board Member of International Journal of Engineering Research and Technology. International Journal of Material Engineering Technology, member of the American Society of mechanical engineers, newsletter editor, secretary, treasurer, program chair, and currently chair-elect of the Energy Conversion and Conservation Division. So the introduction is completely about energy, energy, energy. When I was reading about that, I feel so energized. Thank you so much for that, sir. And so let us please continue with your presentation. And
Thank you. Thank you very much. Actually, that was a long introduction that you gave. Really, I don't know where you got that wonderful write-up, but it's a very long introduction. I would like to just start off by saying, again, you have mentioned I graduated from the same college that you are there in. That was, again, a generation back, I should say. I was in 1975, 1980 batch. Actually, that was a 5-year engineering program in back in the day. And our batch was 4.5 years. So I went to Kharagpur, and then I joined actually BHEL, Tiruchirappalli division. And in Trichy, I was there for 5 years. And then I moved to Penn State in 1987. And then I did not leave Penn State. You know, I finished my PhD, and then they offered me a faculty job. And I have been around Penn State. I didn't see any other place in the United States, in the sense I did not live in any other place. With that background, again, I was working on fluidized bed combustion and new products development there in R&D in BHEL. So I continued in R&D here. And actually, my specialization in Kharagpur was also coal processing. And there were a few people that you are probably familiar in this group. My batchmates are there from that from Kharagpur in that era. So with that background, I joined here, and then I continued my research, as you're mentioning, but the challenges continuously evolve. Let me tell you, that is the main message. You know, typically what we think is, okay, I'm a chemical engineer, or I'm an electrical engineer, I'm a mechanical engineer, or my PhD thesis is in this area, and I'm going to be working in this area. That is the notion that I think evolves or changes over time. That, you know, we need to adapt to the calls that we get from the scientific community, and then adapt our research. But basically, the skills that we acquire in our college is nobody is going to give the same mass transfer problem or heat transfer problem in our life again. You will never see the same problem. But how to tackle that problem or the skill is what you will be using throughout your life. Let me tell you, as you mentioned in my profile, I started off with combustion of fossil fuels and gasification. In 80s, when I went to grad school, we were looking for alternative energy sources because oil prices went up, you know, in those days because of oil embargo, 1973. And so I adapted to coal, you know, coal processing, coal gasification. But later on in 90s, oil prices dropped. So obviously I needed to find a different area. It is not me finding, but there was a call for a different area because the operational problems, fluidized bed combustion, was really taking off, and there were a lot of operational problems, emission problems. For example, fluidized bed combustion, I don't know if you are familiar with or not. It is a combustion method that operates between 800 and 900 degrees Celsius. The beauty of that temperature range is we can take limestone and then put it into the bed, and limestone calcines and produces calcium oxide, and calcium oxide reacts with sulfur dioxide that is produced. and then absorbs the sulfur dioxide or reacts with that sulfur dioxide and transforms into calcium sulfate. That is a solid product. So it can go out with ash. So fluidized bed combustion was environmentally very friendly technology because it could capture sulfur dioxide. Of course, Indian coals are not very high sulfur coals. As you all know, they are, but they are very high ash coals. If you know anything about, if you have gone through any literature about this, they are very high ash coal. They are very nasty coals in terms of calorific value. But since the bed itself is operating at 800 and 900, the nitrogen oxides, which are another set of pollutants that are produced, are also proportional to the operational temperature. And the fixed bed combustion operates at 1200, pulverized coal operates at 1700, 1600 degrees Celsius, and fluidized bed combustion operates at 800 to 900. So when I say it is proportional, so which method produces lowest nitrogen oxide emissions? Fluidized bed. So less sulfur dioxide, less nitrogen oxides, you can put anything that you can think of into fluidized bed, more or less, I should say. So that was a very versatile technology. So I was optimizing in this country because fluidized bed was commercially taking off, and they were using calcium, as I mentioned, limestone. Nobody understood the actual mechanisms. So we tried to demonstrate that the higher the purity of calcium carbonate, which is the limestone, calcite, I mean, it has other impurities, but I'm just trying to simplify the chemistry. If you assume that it is calcium carbonate, it would produce calcium oxide. It would react with one molecule of sulfur dioxide. That's the theoretical chemistry. And everybody, including the manufacturers of the equipment, thought that a higher purity limestone would capture more sulfur. That is not the case in practice. Why? Calcium oxide, when it forms a porous particle because carbon dioxide has come out of carbonate, and it forms porous calcium oxide. But when sulfur comes and attacks, it forms a shell. Why? Because the product is calcium sulfate. Are you guys following what I'm trying to say? So the outside of the particle will form calcium sulfate, and it is solid, and its molecular weight is higher than calcium carbonate. So basically it is blocking all the pores, and so the sulfur dioxide will not be able to get into the particle, inside the particle. So it would go waste. They were not getting the sulfur dioxide. So the reason I'm trying to point out is we went into the fundamentals and changed the perspective. We took 400 tons of each limestone to a power plant, ran the operations as an academic institute, and then demonstrated that with 20 limestones from different parts of the country, and different parts of the state actually at that time, and ran an EPA, Environmental Protection Agency, which is the Pollution Control Board, said, if you go out of compliance because you academicians are trying to do this experiment against the manufacturer's recommendation, we will fine you and close the plant. And with our confidence, we went in and we said, we will take that risk. And ran the plant for 6 months with 20 different limestones, not 99% calcium or purity, but with 53%, very impure, and demonstrated. And then the fluidized bed industry changed their specifications. They did not ask for high purity limestone. The reason I'm mentioning this to you is the challenges will be different. Times call for different challenges. Now, nobody actually knows that they were asking for 99%, because major boiler manufacturers now are using our our equipment. So with that introduction, I'm just trying to give you a message. You need to develop the skills while you are in the school, but you need to have the adaptability to change your thinking, use those skills, and solve the problems in the world. Okay, let me get to the actual presentation that I wanted to give you and show some engineering challenges that we are going to face, and we are facing actually. Okay, so let me share my screen here. Share screen. Okay. Are you able to see my slides? Perfect.
Yes, sir.
Very
Yes,
good.
sir.
Very good. So I'm going to be talking very generic actually here. You can stop me at any time if you have a question. It should be interactive. And if you have any questions, or if you're not following any part of it, just ask a question. I'm not expecting everyone to follow everything because this subject may be new. You might not have learned. Just stop me at any time, okay? Feel free. And again, to talk about the same changes in 2000s, as I said, we were working on that, but now there is another important issue that has come up for the entire world. Your generation has to stand up for that, and that is critical minerals. And I will be talking about that because the high-tech society today needs a lot of these things. Everyone wants the state-of-the-art iPads, state-of-the-art computers, state-of-the-art cell phones, and every year we're all changing these things. This high-tech life will not be possible without minerals. But the first thing that I say clearly to everyone is, if you cannot grow anything, you must mine it. There are only two ways you can get materials. Either you can grow or you must mine. This generation, I'm seeing a lot of people actually come in and say, oh, mining is bad, we don't want to mine. Then put your cell phone away, because without mining, your cell phone will not be there for you. Critical minerals. So right now, the university has, at Penn State, we have established a Center for Critical Minerals, and I'm asked to direct that, to develop that research program here in this country. So I'm, again, emphasizing the adaptability, because that was not my research area in the beginning, but we know what it is because I dealt with ash from fluidized bed and other combustion modes. So I will be giving you some example. Just stop me at any time. I have a bunch of slides I can go on. As a university professor, we don't stop until hour and a quarter. But you know, if you feel bored, just stop me. We can start dancing. I don't mind. Or sing, you know, another song. You know, just we have to be active. All right, folks.
Yes,
So
sir.
let's yeah. But feel free. Again, we have already talked about this part, my background. Let me give you a little bit history of Penn State University. This is a school. It's a big school. It has about 90,000 students. Usmania University, how many students it has? Do you guys know? Entire university.
No.
University campus has about 26,000. So we have about 90,000 here. And our budget is about $7 billion total budget, our university budget. And our research budget, as it says, is about $1 billion. That is 7 lakh crores. Okay, we offer a bunch of programs, 160 baccalaureate programs and 160 graduate programs and so on. So it is a massive school. It is a massive school here. And I want to give you an idea about where we are heading. The first challenge for your generation will be energy, water, and minerals. These are the three things that you will be facing, but I will be talking about two of those three. I could talk about the third one, but we will be sitting here for another 3 hours. So let's examine the world. If you look at this curve that you are seeing, if you look at this curve, how the population grew. This is 1 CE, common era, okay? The whole world, imagine the entire world had about 250 million people. 250 million people. That is about how many? That's about 25 crores, something like that. Yeah, entire world. Okay, it took about 1,650 years to double that population to 500 million. Only 200 for the next doubling, 1 billion people. 1 billion to 2 billion we added in 80 years. 2 billion people we added in, again, 45 years. We added another 2 billion in just about 25 years. And now we are going to be we reached already 7 billion, and we will be, by the end of this century, we'll be touching 10 billion people. What type of curve is this? Mathematically?
Exponential. Exponential.
Wonderful. Very good. You really made my day. Exponential curve. And if you plot the energy consumption of the world, it fits exactly the same pattern. Same pattern. So let's take a look at this. World population grew exponentially. Energy consumption grows exponentially. All right. And most of the population is growing in the developing countries. All right. And so what we can expect is most of the energy growth from now on will be in the developing countries. And 40%, believe it or not, today out of 7 billion, 2 billion people still have not experienced electricity. Have not experienced electricity. Forget about cell phones. They don't know what electricity is. 2 billion people on this planet. It is very hard for us to imagine. And even by 2030, you will see that number, very close to that number still, because population will also increase. All right, so that is the challenge that we're facing. And not only supplying the energy required, and also meeting that energy in an environmentally friendly fashion. So if we look at this is what I'm trying to emphasize. I mean, don't worry about the numbers. North America uses roughly about 270 million BTUs per person. I know that you are not familiar with BTUs or millions, but don't worry about it. It is 270, right? Roughly. No other region per person uses that much energy. And we think that Asia and Oceania, which includes actually Australia here at the last column set, actually they were very much under 2025. Now slowly over this past 30 years or so, we came up to 50, which is, I mean, you don't have to remember these exact numbers, but I'm just trying to say we use what we, in the sense, in India, we are using 1/5 roughly of what this is entire, including some developing countries, including Japan and other places in here. Okay, in India, it is much less. Imagine China is less also. It is included here. So if we were to experience our 4 billion people out of 7 billion people, if we start using the same amount of 250 million BTUs per person, what would be the energy demand for this world? If we're already worrying about the types of energy, we're changing the planet, we are actually, destroying it, it's already, imagine if all 4 billion people in this world get the same kind of lifestyle that West uses. Imagine the amount of energy that we need. All right, let me give you one thing. Listen carefully here. We all want cars. And I have seen this in China. I visited several times China. And of course, I visit my own country in India. And I talked to OUCT people a couple of times, students. I gave seminars, and I gave seminars throughout the country. It is very difficult to communicate the importance of this. Vehicles per 1,000 people. Vehicles per 1,000 people. If we look at that number, when was the first automobile made? 1903, commercial. Okay, if we look at the way it grew in the United States, because that's where the Ford Motor Company started, and it grew like this. Over 1 century, the ownership went from up to about here right now in the United States, we have about 870 cars per 1,000 people. 1,000 people. People including the child and a 99-year-old. If we look at licensed drivers, we have more cars than licensed drivers in this country. All right. Okay, so how did we get here? It took right from this, and now I'm going to show you. This is the key point. Pay attention to this. Eastern Europe in 1998 is where United States was in 1925, in 1998, in terms of ownership. In terms of ownership, Eastern Europe in 10 years, it went up to this point, 300. Western Europe, developed part, they are still there at 500. Okay? Western Europe, this is Canada. This is Western Europe in 2008, 600, roughly, closer to 600 ownership. And they were where United States was in 1980. All right? Canada, 2008. You may say, well, whoa, wait a minute. I don't care about these countries. Tell me something about India, China. All right?
Yes,
they're
sir.
not even on the scale right now. So let me show you, actually. I'm going to change the scale here. What did I change? Vehicles per 1,000 people y-axis. It is only 160. And you can see the year. Of course, this is year corresponds to United States development. So this is the curve. I truncated it up to 160 vehicles. Eastern Europe is right here, which is the highest number that we have seen on the previous graph. And here, Africa in 2008 and 1998 is where, right now in 2008, is where United States was in 1919. That is the First World War. Okay? Now, why are you talking about this, you may say, right? Okay, let's go and see. Brazil, 2008, 1998, South Central America, Middle East. China, 1998 was about 10 cars per 1,000 people. By 2008, there were about 30, 35, right? You may wonder, okay, what is your expectation in 2018, 2 years ago? Must be somewhere here. Where is India now? India in 1998 and 2008. In 2008, folks, you were still young in school, probably, right? Maybe elementary school or middle school or whatever it is, you know. Where is India in 2008? It was where United States was in 1919, around that time, First World War. Okay, no. Now there are several companies that have come and we are manufacturing cars everywhere. Okay, I agree. You know where we moved? We moved to this place. This is in India. This is in India. Where is it? Bangalore. With this kind of cars. All right. Our goal is to reach United States, right? Or Western world. Where are we going to put these cars? Where can we drive? You know what? In India in 2018 is right here. 41 cars for 1,000 people. If I challenge you, all of you, I'm so rich in this world, I can give one car to everyone. The whole India, where are you going to put? Where is the oil? How can you drive in on those roads? That is the challenge that I'm posing to you. This China actually in 2018 is 270. Believe it or not, 270. It was here and it went off the scale right now, China. But they are facing hell of a problem actually right now. They cannot drive. The same thing. All right. So my question is, we're going to need more liquid fuels. We may say, well, we may say, oh, we are going to be using a lot of solar energy. We are really doing a lot of energy. Solar energy is not driving cars anywhere, actually, right now. Okay, so we need a lot of liquid fuel even in 2040. So that will emit CO2. And I'm not going to talk about all this. That is a major, major challenge, folks, for you. We need to come up with a transportation system. You guys have to totally revolutionize, think in a different way how to transport people rather than follow the West and give license to 40 more car manufacturers. It is not a solution. It is not a viable solution, I should say. All right. So let's see. The challenge is how to curtail the CO2 emissions. From power plants, yes, we can go to solar right now. If we get energy storage, we can put it into storage and then use it for transportation, charge batteries and use. How many electric cars are there in India? So consequences are this. Let me tell you, we are actually sinking. The planet is sinking completely in water right now with CO2 emissions. 650,000 years, if you look at, nowhere, there were peaks, there were, there were humps and bumps, you can see in the history. And believe it or not, when the CO2, average CO2 went down by 100 parts per million, we went into ice age because 8 degrees temperature difference was there. If we go up from 280, that is the pre-industrial level peak, 280, 100 parts per million up to 380, 8 degrees temperature increase you would see. Right now we have seen only 1 degree yet. If this logic applies, we should see 8 degrees temperature increase. That will fry the planet, fry the planet. And we are already at 2014, 420, not 380, 420. Never ever this planet has seen, of course, planet has seen even much higher concentrations actually. If you look at history, millions of years ago, there was very high concentration of CO2, but there was no human being on this planet. So your challenge will be actually protecting our planet. Anything that we do in engineering, we should see the overall, carbon footprint, not just the process. Oh yeah, I designed a beautiful product. What is that product going to do? All right, and how much we're going to emit. Again, I'm not going to, this is absolutely not sustainable. It is not sustainable because if 4 billion people that we talked about if they see the same lifestyle that we are aiming at, like West, this CO2 will be skyrocketing. Skyrocketing. There are models that show that. Impact, I'm not even showing. You are experiencing that there. World's worst, the 5th in the world is India here in terms of air pollution. Okay, average air quality, if we look at. Okay, and air pollution also reduces the crop production. That is important to feed the people. Okay, and you know where I'm sitting right now and lecturing this or talking to you? State College, Pennsylvania, air quality is 10. Okay, so options, what can we do? What are you people need to keep? Efficient extraction, resource recovery. Obviously, anything that we do, we need to make it more efficient. You know what the average efficiency of a power plant is? Anyone?
About 30%.
Very good. Very good. In the ballpark, actually. Yes. The super efficient power plants can produce 42%. Super efficient IGCC plants. So in spite of that, 58% is going into the environment. So if we can save 1 BTU, not burn, you are not only saving that 42% efficiency plant, also you're not emitting that 58. Reduce the carbon intensity, improve efficiency, go for renewables, go for nuclear, and go to carbon-free energy, and try to control the demand side and supply side. I'm not going to go into everything, but I'm just going to explain you, or we need to take the CO2 out and put it into the ocean, or put it into the ground, or put it into somewhere nobody sees. Planet doesn't see. Again, these things are also being explored. A lot of people are exploring. And we also looked at in our own group, actually, carbon sequestration, reduce population so that energy demand will not be there. Of course, part of it is done by Corona, but still that is now nowhere near, unfortunately. Population control is not in our hands. It's a social change. Stop, reduce growth. It is very unfair for 40% of the population not to see energy and rest of the people enjoying. It is not fair. They also need to come up. So this is not a choice. Everyone wants to have the high quality life. So there are a lot of consideration. It is not just engineering. So let's look at the renewable energy portfolio. People are talking about it. Our Prime Minister is talking about it. Solar energy, wind energy, everything wonderful. This is all great. It takes 700 gallons of water to produce 1 gallon of ethanol, because you need to grow something. Crops don't grow just like that. It takes water. Where do we have water? Biocrops. It is a very difficult thing. Solar and wind, large land requirements. Hydro, limited places. And we also, water requirements are a problem for biofuels also. And also biofuels is food versus fuel. If I grow ethanol, I get much more money because I can sell it as fuel. But I'm converting the area to grow something that makes money rather than feed people. Okay, that is its moral issue. Now, solar and wind energy. By 2040, everyone is aiming to get high solar, but not 2040, actually. If given a choice, you all want everything to be run by solar energy. But solar energy comes at a very fixed amount, density, onto this planet. So even in 2040, the projections are there will be coal, gas, nuclear, and there will be other fuels that will be used, but there will be solar energy that will grow. These are all projections again. We don't know what will happen. But let's look at the positive side. Let's look at the positive side. If we go for solar, if we go for everything electric and generate that electricity from renewables, what are the options? Solar, wind. Solar, wind. Those are the only two options that we have, because we have so many water, flows or rivers that we have, and we can only build so many dams. Hydro is not an option there to increase. Nuclear is an option, but nobody wants to go nuclear in the world. There are problems with that. So if we have clean capacity, like India aims at 60% renewable energy by 2030, excellent, excellent. All right. But how do we get solar energy? We need solar panels. What do we use for solar panels? Silicon and indium, gallium, all these metals that we need to use, and superconductors, a lot of copper that we need for this, aluminum. Where do we have this? Do we have that? And Siemens is building beautiful Beautiful, 14 megawatts offshore wind energy. They have the designs ready. In 2024, they're going online, actually. They're putting up this one. 14 megawatts, unbelievable. One, and the size of this is, the area that this windmill sweeps is 39,000 meters square. That is 10 acres. Each windmill sweeps. It's an amazing design, accomplishment. However, what are the materials that go in? I just want to touch upon this. Solar panel uses bauxite, uses arsenic. It is mined in China, Chile. Copper, United States, Chile, Peru, China. Molybdenum, you see the countries that are producing these. Gallium, China, Germany, Kazakhstan. Indium, China, Japan, Canada, Belgium. Iron ore, yeah, India is there in here too. Bauxite, aluminum is there. Selenium, again, Japan, Belgium, Canada. All right. It is not, I'm not talking about just India. I'm talking about United States. This lecture I gave to you, this material is common. That's the reason I am now heading this center to develop these kinds of things. What is the best way to get these things? If you take a windmill, who are we depending on? Mined in Congo, this country is very unstable. All right, China. There are a few here. Zinc, iron in India here. Gypsum is again China. Molybdenum, copper. Now let's go to electric vehicles, folks. This is the future, right? Wow, exciting. Really exciting. Elon Musk, wow, Tesla, right? What wonderful. See, I tell with very sad thing, actually. In the United States, we talk about graphite, carbon, form of carbon. We import 100% graphite in the United States. Cobalt, it's coming from Dominican Republic of Congo here, China. Manganese, nickel. I don't have to go through everything here. Lithium, which is the crucial thing, actually. Cobalt, graphite, lithium are very crucial. Cadmium, these are all used. Ring bells, right? These are all used in batteries. In future, we need storage because wind blows at night. You need power in the morning. Sun is not there in the evening. You need to store it. So, smartphones. Every year, iPhone comes up with a new model. Throw the old one, buy a new one. All these things use, basically these very rare metals. Do we have them in ground? And how do we get those things? It is not like coal. You go and get tons and tons. These are in parts per million. You need to process several millions of tons to get a ton. 10 tons, particularly when it comes to renewable energy. Wind turbines, blades, because they have to be stronger and stronger when you are sweeping that much area. Obviously, the force that acts on it is tremendous. You need to have materials that are stronger. So if you blend a little bit of scandium with aluminum, the strength goes up tremendously. So we are actually going for those kinds of things. And magnets, power windows. My car has power windows. My car has everything, right? And, my seat, how does it happen? There are motors everywhere. Motors have to be smaller and smaller, more powerful. How do we use those? Magnets, neodymium, boron, iron. These are the ones. Neodymium is the critical mineral that is used in magnets, sophisticated magnets, very powerful magnets. Solar energy, we have already seen arsenic, gallium, germanium, indium. Electric hybrid vehicles. I own one of these Teslas, actually. It's parked right in my garage right now, Tesla. But you know that freaking thing, you know how much it uses? Rare earth elements. Tremendous amount of, 26% of car weight is battery, 26%. Okay, and what we need in that is neodymium, dysprosium, because these are batteries, motors, everything. It's all computer control. There is nothing in there other than wheels, battery, software. Rest of it is shell. There's nothing in there, actually. Defense applications. If we go through all defense uses, actually critical uses, night vision goggles, everything that military needs, we need rare earth elements. Okay, and where are these coming from? I mean, this is again particularly the market, US vulnerability and the world vulnerability, I can say. If I have 35 elements here, it's very difficult for you to see, but I'll blow it up. And this is the percentage that we import here in the United States. And 16 of them, actually, if you look at the top here, 100% we import, 100%. And then over 50%, if we import it, is called critical element, because somebody else is controlling our destiny. Okay, let me show you clearly here. Now you're able to see. Are you able to see the red on this graph? Yes, you don't need to really read this, but all red is China, period, done. You don't need to even know. So all these elements that we have here listed are coming from China. 94% of the world's market is controlled by one country. I hear through all these WhatsApp messages, let's bar China. You know what they can do? They can squeeze us like this here. You think that they will sit quiet on the side and say, okay, guys, you don't use Chinese products, no firecrackers or no this, no that. And okay, we don't make anything and we just sit aside. They will control the defense part of it, especially in the United States here. So China basically gears up to weaponize the world, actually. They can blackmail the whole. So our goal here is White House has issued, forget about White House, mess today, but in general, the government is very keen on developing these things here itself. And my goal is here, from the university side, we are developing this. And what about India? Look at this. This is 2018 Deccan Chronicle. Are you guys familiar with Deccan Chronicle?
Yes.
Yes, sir.
Yeah, indium, gallium, 500 times more. And if you look at this, indium supplies would be only 14 years for India. So indium, gallium for solar energy. Our prime minister wants by 2030, everything solar, but where is the material? So which means we have to import. We can do it, but we have to import. Where do we get it from? We cannot make it in India. Minerals, we have to get it from outside. So the search is basically to find these critical minerals. Basically, the ores are bastanite, monazite, xenotime, and apatite. Mostly they are monazite, xenotime, and bastanite are the ones that apatite is not used. So basically one is carbonate, the other one is phosphate, and this one is also yttrium phosphate. Here, lanthanum phosphate, okay? And what we are trying to do here is we may or may not have all the resources here, all the ores here, but we are trying to use secondary sources. Coal has ash. Coal has, believe it or not, the ash has almost all the elements that we know of in the ash, different degrees, different amounts. So that's what we're exploring in the production, in mining, in separations, coal refuse, coal middlings, water resources. Looks like one of my classmates is there on the list here. He can recognize some of this, but clean coal, feeding coal, energy conversions. When you burn it, you get fly ash, bottom ash, right into the boiler, which is basically goes in the form of ash. Fine ash is fly ash, and the bottom ash is the one that comes out at the bottom. Everywhere we can recover some of this. Believe it or not, we're not mining anything extra. It is the waste product from a power plant. If you guys can come up with a method to actually extract some of these things, you could be billionaires. Who is the richest person today on this planet?
Elon Musk.
Elon Musk. That's very good. Elon Musk. Not Bill Gates anymore. You have to have vision. You can do it. All right. And I'm also looking at waste utilization. This is overburden, preparation refuse, fly ash, flue gas desulphurization residue. All these things have a ton of this material. And also in the United States, we are using, we need lithium anyway. Lithium is a very critical mineral, but when we use fracking to get the natural gas out, that fracking water actually in oil and gas industry, you get that water which is coming from the ground as wastewater has lithium in it. We can use that lithium. We can extract that for battery materials. Okay. All right. We talked about wind energy. We talked about solar energy. Solar power plants and windmills last only that long. So long. The problem is this now, folks. We build stronger and stronger materials. They cannot be recycled. They cannot be broken down. They cannot be used for recovery. Millions of these things, tons of these materials will pile up, are piling up right now on our land here, and we're basically putting them in landfills. Is that a good thing? Because they're not biodegradable. So yeah, it's renewable energy, but at the end of life, it's like nuclear energy. We can build a plant. After 40 years, we have to bury that plant somewhere. What do? Because it is made up of fiberglass, and to make these materials stronger and stronger to withstand high winds, we are using these rare metals in them. They're not easily broken down. So the challenge is actually, let me come to chemical engineering operations, how we can extract, what it takes to extract these things, the challenges. First of all, we have to find a material that has highest amount, and then we have to grind it and and we use today very caustic, very strong acids and bases to get these materials into liquid. Once they get into liquid, we have to separate, because neodymium, praseodymium, iron, everything, not just these rare earth elements. We get iron, we get calcium, we get aluminum. Everything comes because we are using very powerful acids on the soil, environmentally destroying. So once we get those things, we need to separate, develop basically processing, what kind of machines we need to use to grind these things, and then what kind of acids we need, and how much we need. And then ion exchange, mass transfer. And we use a lot of actually here extraction, liquid extraction methods. And after that, we get these materials. And if they are not economically viable, Chinese will come and they will undercut the price because their government can do it. And our industry will be flat in a capitalistic society. Our meaning here in the United States. That's how they kill the solar industry here.
Dr. Sharma?
Yeah.
Can we, ask the students for comments?
Absolutely. Anytime.
Okay. So
comments, questions, anything exciting, anything lousy. Yep, sure.
So why don't you guys start talking a little bit? Tell, a couple of you start saying what you thought till now. What are your thoughts till now? Okay, Nikhil, go